Next is fluid dynamics. It is the study of fluids in motion. Therefore, we write that fluid dynamics is a study of fluid in motion, and this motion is called a steady flow if satisfy the following condition. Number one, the velocities of each particle at a given point remains same or constant in time. Second is that each particle of the fluid follow a smooth path and path of particles do not cross each other. Third is the path taken by a fluid particle under a steady flow is called a streamline, and it is defined as curve whose tangent at a point is in direction of fluid velocity at that point. So we can draw a typical path of the fluid particle whose velocity is given by the tangent at a point. So at point P, Q, R, we have drawn the tangents which gives the velocity and its direction at these points. Similarly, we can draw a region of streamlines like the region P, Q, and R, and there are the streamlines. These streamlines do not cross each other. From conservation of mass, we can write that mass in a region will be equal to mass coming out of the region. This implies that mass entering at the region P will be equal to mass entering at the region Q will be equal to mass entering in the region R in time, say delta T. This implies that density at the region P into volume of the fluid, that will be equal to the density at the region Q into volume VQ, and it is equal to rho R into VR. This volume will be equal to the area of the cross section of the region multiplied by the velocity of the fluid, and distance covered by fluid in time delta T will be V delta T. So volume is given by A into this length, that is V into delta T. So replacing, we will have rho P into volume will be AP, this is the area of cross section at the region P, into velocity of the fluid at the region P into delta T. This will be equal to rho Q into AQ into VQ into delta T, and it will be equal to rho R into AR into VR into delta T. And because delta T is common in all these three terms, so we will have rho P AP into VP, that is equal to rho Q AQ into VQ, and it is equal to rho R into AR into VR. For incompressible fluids, we can say that rho P will be equal to rho Q will be equal to rho R. That means density of the fluid remains same for incompressible fluids. This implies that we will have AP into VP, that is equal to AQ into VQ, and it is equal to AR into VR. So we can conclude that A into V, A is the area of cross section and V is the velocity of the fluid. In this area of cross section, it is a constant. This is called equation of continuity, and it is applicable for the fluid which is incompressible, and it is a statement of the conservation of mass. This AV is called volume, flux, or flow rate. Flow rate means amount of fluid, that is volume of fluid flowing in 1 second. Therefore, using the equation of continuity, which we have discussed, is the product of area of cross section and velocity, and this product is constant. That means if this is area of cross section A1 and another is A2, then the velocity at area of cross section A1 is V1 and A2 is V2, and from equation of continuity, A1 V1 will be equal to A2 V2, and we can conclude here that speed of fluid is greatest where cross-sectional area is least. So from the figure we can say that A1 is greater than A2. This implies that V1 is lesser than V2. Second is streamlines are closer where speed is higher. So in the figure, streamlines are closer for the area of cross section A2 because it is smaller. Similarly, we can say that when a liquid or the fluid flow from the area of cross section A1 to A2, its velocity increases. That means because V1 is less than V2, this implies that velocity increases. It means there is an acceleration in the fluid, and this acceleration is caused by pressure difference. Let's take some problems. First question is, water falls from a tap down the streamline, area decreases, area increases, velocity remains same, or area remains same. When water falls from the tap, then velocity initially is 0 and it comes down, and depth increases, its velocity start to increase depending on the acceleration due to gravity and the depth. Therefore, using the equation of continuity, which say that area of cross section into velocity remains constant for incompressible fluids. Therefore, as the water from the tap come down, its velocity increases. So if velocity increases, then area of cross section will decrease. Hence, option A is the correct option. Second question is, in a streamline flow, a streamline can be drawn as shown in figure, and for a particular point, say P, velocity is given by the tangent at that point, and all the particles passing through this point of the streamline will have same velocity, that means same magnitude and same direction, while they may differ at different points. So option A is the speed of particle always remains same, because speed may differ at different points, so the statement is false. B is the velocity of particle always remains same. It is also false because velocity may differ because of different magnitude or directions. C is the kinetic energy of all particles arriving at a given point, this is the particular point, are same. So at a particular point, the velocity, that means magnitude and the direction of all the particles remain same. Therefore, kinetic energy, which is half mv square, will also be same. Therefore, this statement is true. And option D is the momenta of all particles arriving at a given point are same because momentum is defined as product of mass and velocity at a point for all particle is same. Therefore, momenta of these particles will also same. Hence, D is also true. Therefore, option C and D are the correct statement. Third question is, the cylindrical tube of a spray pump has radius r, one end of which has n fine holes, each of radius r. If the speed of the liquid in the tube is capital V, the speed of the ejection of the liquid through the hole is. Using the equation of continuity, we know that product of the area of cross section and velocity coming out of this area of cross section is constant. In the given situation, A1 V1, where A1 is the area of cross section of the tube and V1 is the velocity coming out of it, will be equal to A2 V2. A2 is the area of cross section of the fine hole and velocity coming out of the fine hole, and there are the n holes, so multiplied by n. This implies that A1 is pi r square because r is the radius of the spray pump into velocity is capital V. This is equal to n into A2 will be pi into small r is the radius of fine hole, so it is pi r square into velocity V2, which we have to find. This implies that because pi is common on left and right hand side, so get cancelled. This implies that V into r square equal to n into r square into V2. So V2 will be equal to V into r square divided by nr square. Hence option D is the correct option.